So inshallah आज हम इसको we will finish the syllabus of functional analysis. फिर हम उसको ज्यादा टाइम दे पाएंगे डिफरेंशियल ज्योमेट्री को. So सभी कैमरा ऑन करो. 12 ही है आज, क्या बात है. Okay, let me share the screen and do our last theorem basically of our syllabus. Okay, लेकिन मुझे लगता है एक आध चीज रह गई है, वो देखेंगे इसके बाद. Okay. Okay. Let's state what we call the spectral theorem for finite dimensional spaces. Spectral theorem. There are many theorems जिसको हम spectral theorem कहते हैं. जो हमारा है that's for finite dimensional Hilbert spaces. And by that we state this: every normal operator on a finite dimensional inner product space, finite dimensional inner product space, so let's call that H over C, is diagonalizable or diagonalizable. By that I mean we can find a basis of consisting entirely of eigenvectors of T of that normal operator. ठीक है, चलो तो इसका जो proof है, we would need a few lemmas to prove the theorem. So the proof of this theorem would depend upon the following lemmas. Yeah, for the proof of this theorem, we need the following lemmas. So lemma 1 is this: if T is a normal operator, and by normal operator you should know that normal operator matlab hai it commutes with its adjoint. T star T is equal to T star. Now if T is a normal operator on an inner product space H, inner product space H, then lambda is an eigenvalue of T if and only if lambda bar, means the complex conjugate of lambda, is the eigenvalue of the adjoint of T. Of course, with the same eigenvector. तो इसको हम प्रूफ करेंगे, proof lemma 1 का. Now what we do for all lambda belonging to the set of complex numbers we have, by the definition of the adjoint, it should be T minus lambda I adjoint is T adjoint minus lambda bar I, क्योंकि I adjoint is I. So therefore T minus lambda I into T minus lambda I bar is the same thing as T minus lambda I multiplied by T minus t minus lambda bar, t star minus lambda bar I. And if we multiply that, so this would be t star minus lambda bar into I into t. Because it commute nahi karta, so I have to keep that in mind. Okay. So this lambda bar t, ठीक है. Lambda bar t into I. Then I would have minus lambda I into t star minus plus lambda into lambda bar I into I. So of course, this is just an eraser. And ये बराबर होगा t star minus lambda bar into I into t, because t into I is identity, so इससे फर्क नहीं पड़ेगा. Minus lambda into t star plus I think lambda into lambda bar into I. Because identity को 10 बार भी लगाओगे तो it's as good as applying it just once as a map. What I do, अब मैं इसको चूंकि it's a vector space, so we does commute. So if I take t star out of this and this, what do I get? I will get t star. चलो बजाय ऐसे लिखने के, नहीं पहले मैं इसको लिख ही देता हूँ. मैं इसको लिखता हूँ t star t minus lambda bar t. या तो यहाँ मैं फ्लिप करूँगा minus lambda t star. Okay. Plus lambda bar I. I have used that t is normal. So t star is equal to t star t. जो ना मैंने यहाँ लिखा है. Then I can take t star out of these two, but it is the same thing as t star into t minus lambda I. क्योंकि मैं इसको I से मल्टीप्लाई करूँगा तो कोई फर्क पड़ेगा नहीं. Then इसको और इसको मैं लेता हूँ इन दो टर्म्स को. इसमें से मैं क्या निकाल सकता हूँ? lambda I, lambda bar I. अगर मैं lambda bar I निकाला तो it should be t minus lambda I. Lambda bar into lambda, scalars तो commute करते ही हैं. But then this would be equal to t star minus lambda bar I multiplied by t minus lambda I. That would be actually t minus lambda I star. चलो मैं ऐसे लिख देता हूँ. अब ये जो तुम recognize कर रहे हो इसके साथ, so then I can say that is t minus lambda I into t minus lambda I star is equal to t minus lambda I whole star multiplied by t minus lambda I. कहने का मतलब अगर t normal है तो t मतलब it commutes with its adjoint, this operator. So अगर t normal है, हमने प्रूव किया t अगर normal है तो t minus lambda I भी normal है. It implies that t minus lambda I is normal. That is, यहाँ मैं लिखूंगा t minus lambda I is normal for all lambda belonging to C. अगर t normal है. But this is equivalent. So this would imply this is if and only if normal operator के साथ हमने शायद ही प्रूव किया था कि it preserves any t minus lambda I times x in norm is equal to t minus lambda I star applied to x. The normal operator, now that's the same thing as saying normal operator is an isometry. यानी हम ऐसे लिख सकते हैं, और हम इसको प्रूव करेंगे, है ना? And a norm of tx is equal to norm of t star x would be true if and only if norm of tx square is equal to norm of t star of x square. Using the inner product, this would be true if and only if tx inner product is equal to t star x. And using the definition of the defining property of the adjoint, this would mean x t star t of x is the same as x t star of x. And then shifting जैसा कि हम इससे पहले कर चुके हैं यानी x comma t star t minus t star applied to x is equal to 0 for all x. अगर ऐसा true है तो this must be a zero vector यानी you would get t star t is equal to t star यानी ये commute करता है मतलब इसको reverse भी कर सकते हैं अगर t अगर ये normal है which is the same thing as t is normal. अगर t normal है यानी वो अपने इसके साथ commute करेगा then this is true then this is true then this is true then this is true. तो वो मैंने यहाँ पे कर दिया कि अगर ये commute करता है अपने adjoint के साथ then this must be true. Therefore, if t minus lambda I of x is equal to 0 for some x not equal to 0, it would be true if and only if t minus lambda I star of x is equal to 0. क्यों? क्योंकि of course अगर ये 0 है तो इसका norm 0 है और अगर norm 0 है तो vector 0 है. So अगर norm of a vector is 0 if and only if the vector is 0. So this is what I get. That is, इसका मतलब है that is t of x is equal to lambda x if and only if t star of x is equal to lambda bar of x. So जो कि हमें प्रूव करना था. That is अगर lambda eigen value है t का तो lambda bar eigen value है t star का if for a normal operator. So that finishes our lemma 1. Let's go to lemma 2. शुरू lemma 3 था इसमें शायद नहीं. lemma 2 वो ये है eigen values corresponding to distinct eigenvectors. Eigenvectors corresponding to distinct eigenvalues of a normal operator. Are orthogonal. हमने किया था eigenvalues corresponding to distinct eigenvalues of an operator are linearly independent. लेकिन अगर वो operator normal है तो it's much more than that. They are orthogonal. Orthogonal are always linearly independent. वो हम किसी जगह prove कर चुके हैं. So let's do the proof of this. It's again very simple. Let x1, x2, comma to xk be eigenvectors corresponding to distinct eigenvalues x1 comma lambda 1 comma lambda 2 up to lambda k of t, where t is the normal operator. Then for I not equal to j, यानी अगर I j के बराबर नहीं है, lambda I minus lambda j as a scalar multiplied by the inner product xi xj can be written as, I can write it as lambda I into xi xj minus I should write lambda j xi xj, right? That can be written as lambda I xi comma xj, but I can write here it as minus xi lambda j bar xj, but then that can be written as t of xi, because lambda I is the corresponding eigenvalue, इसका corresponding eigenvector xi है, comma xj, minus then I can write xi, यहाँ मैं लिख सकता हूँ t star of xj, isn't it? Of course, है ना? Because जैसा कि by lemma 1 lambda I अगर corresponding eigenvalue है t का, तो lambda j bar t star का है by lemma 1. But that can be written by the defining property of this eigenvalues. This is the same thing as minus यहाँ रहेगा. This is the same thing as t of xi comma xj, but that is the same thing, so this is 0. Now since I is not equal to j, क्योंकि ये distinct है, lambda I minus lambda j cannot be 0 because they're distinct. ये प्रोडक्ट 0 है और ये नंबर 0 नहीं है, उसका मतलब ये नंबर 0 है. इसका मतलब हुआ xi comma xj is equal to 0 for all I not equal to j, which implies that x1 comma x2 xk, मैं सीधे ब्रैकेट में डाल रहा हूँ, are orthogonal. तो ये लेमा 2 हो गया, बस हमें यही चाहिए था mainly. Now we come to the proof of this here, and we would use the induction. Now, चूंकि हमने कहा था finite dimensional जो हमारा theorem था, finite dimensional product space H, so let us assume its dimension is n. Basically, we will do it the induction के जरिए. Now, assume that dimension of H जो है वो n के बराबर है, of course जो less than infinity है. Now, if n is equal to 1, if it is a one-dimensional vector space, the result is obvious. The result is obvious. एक one-dimensional vector space कैसी होगी? Would be some lambda times then h बराबर होगा lambda times x naught, where lambda is any scalar and x naught is some non-zero vector. तो इस टाइप की हो, scalar multiples of a non-zero vector. Now, obviously इसकी जो basis होगी वो कोई भी non-zero vector तुम पकड़ सकते हो, इसकी basis होगी. So x naught जो है, this is the basis of h, and of course ये मतलब x naught is also the eigenvector, because what? Should I write it like this? Okay, चलो अगर n1 है तो इसको हम ऐसे लिख सकते हैं. So what would be t of, अगर कोई x यहाँ belong करता है, now t of x जो है वो होगा lambda, चलो लिख सकते हैं t of lambda x naught, which can be written as lambda t of x naught. So I can write this as, should I write it like this? Lambda times x से आएगा. T is linear. I want to show that for dimension 1 it's obvious. तो अगर dimension 1 है तो ये इस type की vector space होगी, that's fine. Scalar multiples of a singular vector. So the T is a map from H to H. So what do I get? तो T of x जो होगा वो खुद भी कोई scalar multiple of, ऐसे कर सकते हैं. T of x जो है वो belong करेगा H में ही, तो T of x भी होगा, let's write some beta times beta times x naught, but that would mean that t of alpha x naught is equal to some beta x naught. वैसा ही होना चाहिए for some alpha beta belonging to C. So that would, using the linearity, that would amount to saying, I want to write it as, that would be t of x, when my acidic is equal to, I can write it as beta divided by alpha into alpha times x naught. That would be lambda times x. हो गया, तो हमें मिल गया ये जो अल्फा टाइम्स एक्स नॉट है, इसको हम आइगन वेक्टर मान सकते हैं, किसी भी एक्चुअली वेक्टर को हम आइगन वेक्टर मान सकते हैं, हर किसी वेक्टर का एक्शन ऐसे ही होगा. So there is essentially nothing to do. I've got a basis element consisting of eigenvectors. Yes, चल जाएगा. Okay, now let's come to the main thing. So, assume that the result is true for, assume that the result is true to true for all inner product spaces, all inner product spaces of dimension less than n, dimension less than n, and we show that it's also true for inner product spaces of dimension n. So by principle of mathematical induction, then it must be true for all inner product spaces having finite dimension. Okay, now let lambda naught be the eigenvalue of t, eigenvalue of t with x naught as an eigenvector, with x naught as an eigenvector. और हमें पता है इसका होता ही है eigenvalue, because finite dimensional space में every operator has an eigenvalue. So let lambda naught be one of those and x naught be the eigenvector, the corresponding eigenvector. So that is t of x naught जो है is the same as lambda naught x naught. ये हम मान के चल रहे हैं. Now put m be equal to span of this one dimensional space, the span of linear span of x naught, all scalar multiples of x naught. Then हमें पता है what we call projection theorem. It says that we can divide it into, but m perp is then the kernel of the projection onto m, तो इसकी dimension होगी n minus 1, क्योंकि of course the dimensions have to add. So m perp की dimension n minus 1 है, यानी orthogonal complement of m, क्योंकि इसकी dimension 1 है. That's because dimension of m is equal to 1. तो m perp की dimension होनी चाहिए n minus 1. So therefore it must be true for this m perp. But before that we have certain, मतलब ऐसा हमने किया, मेरे पास h है, यहाँ पर भी h है, ठीक है ना? So I'm saying that t is a linear map from this to this, and t is normal, and I have to show that you can find the basis of h that consists of the eigenvectors of t. अब मैंने क्या लिया, इसका मैंने एक हिस्सा लिया जिसका मैंने m रखा नाम, इसकी एक सब स्पेस, राइट, और ये इसका m perp है, दो हिस्सों में डिवाइड किया, इसकी डायमेंशन n minus 1 है, इसकी डायमेंशन 1 है. Now what I do, I would show that t would send m to m, t would send m to m, t would send m perp to m perp, यानी यहाँ पर भी है ना m perp पर m, लेकिन ये जरूरी नहीं है कि t जो है वो m perp के हर वेक्टर को m perp में ही भेजे. But we will show that if t is normal, then it would send m perp to m perp, and then I can think of this t restricted to m perp as a map from M perp to M perp. यानी I can just disregard this M part. तो वही हम करेंगे. We claim that M purpose इसको हम कहते हैं invariant and T and T star. दोनों ही हम दिखाएंगे. And T M perp is contained inside M perp and T star M perp is contained inside M perp. Of course, T star is also a map here from H to H. So that is the main thing. अगर हमने ये prove कर लिया तो we are done. So let's start. Let X belong to M perp and Y belong to M. Then मैं लेता हूँ T of X. T of X कहाँ belong करेगा? यहाँ पे. और मैं दिखाऊंगा it is orthogonal with Y. So TXY is the same as XT star Y. अब चूंकि Y जो है वो M में है. M क्या है? M is span of X naught. So it means that this would be XT star of some alpha X naught. Because it would be some scalar multiple of X naught. लेकिन T star तो linear है, so it would be alpha T star of X naught. Now furthermore, I also know that मैंने किया है कि T star के it's the eigenvector corresponding to the eigenvalue lambda naught, यानी ऐसा. And this must be then equal to X alpha lambda naught X naught. But I can take them out, so you will get bar. यहाँ हमने use किया by lemma 1. lemma 1 में ये था कि अगर T of X naught is then T star of X naught जो होगा that will be equal to lambda naught bar X naught. That's lemma 1. Because T of X naught is lambda naught X naught. अब इसको बाहर निकालेंगे तो यहाँ पे lambda naught आ जाएगा, alpha bar आ जाएगा और X naught आ जाएगा. लेकिन X है M perp में, Y है M में, तो ये दोनों छोटी ऑर्थोगोनल है, तो ये तो 0 होगा. इसका मतलब क्या हुआ? इसका मतलब जो है Tx जो है यहाँ पे वेक्टर और Y के हर एक M के हर एक वेक्टर के साथ इसका इनर प्रोडक्ट 0 है. Therefore T of X must belong to M perp, which implies that T of M perp is contained inside M perp. How about T star? Now again, let X belong to M perp and Y belong to M. बिल्कुल ऐसा ही चलेगा. So you take T star यहाँ पे, T star X comma Y then would be equal to X T of Y. अब चूंकि ये M में है, so that would be X T of some alpha X naught for some alpha belonging to C, that would be equal to X alpha bar T of X naught. अब चूंकि इसका eigenvalue है, so this would be X alpha lambda naught X naught. That would be of course alpha bar lambda naught bar. तो अंदर बचेगा X naught, क्योंकि X M perp में है, Y X naught M में है. Because M is the span of X naught, that would be 0. Which would imply that T star X जो है वो M perp में है, and hence T star of M perp is contained in M star. So now, if we restrict S is the map restricted to T M perp. तो मैं S उसका नाम देता हूँ. Then S is a map from M perp to M perp. Isn't it? Because it preserves this domain. It's invariant. So I can just define this now as a map from M perp to M perp, which is now an operator, a bounded linear operator. And so सकता हूँ S belongs to the bounded linear operators M perp और इसकी dimension तुम्हें पता है M-1. यानी S के लिए true है अपना result. Okay. And you can find a basis of M perf which are the eigenvectors of S. You can do that now. Now furthermore, हम S star देख सकते हैं. Now further, for all xy belonging to M perf, where मैं सोच सकता हूँ S as a map from M perf to M perf, x S star y. तो अगर S है तो S star भी would be also a map from M perf to M perf, defined by इसकी जो defining property है वो ये है. You would have this would be equal to Sx comma y, but that would be equal to Tx comma y. Why? Because S is just the restriction. S is the same as T, only the domain is restricted. But that by definition would be x T star of y. That means it implies that x S star y minus S star y, मैंने गलत लिखा, T star y, is equal to 0 for all xy belonging to M perf. So M perf is a inner product space. So the x के साथ सारे x's के साथ इसका inner product 0 है. It means that S star y is equal to T star y for all y belonging to M perf, or in other words, S star is nothing but T star restricted to M perf. क्योंकि जब मैं डोमेन को M perf रखता हूँ, they are essentially the same. So यानी इसका मतलब ये है, ये जो M perf है, it is invariant even under the adjoint. M perf is invariant under the adjoint and the T star. कहने का मतलब ये जो मैंने मैप लिया था ना, ये M perf है, ये M है, ये जो T star है, इसको जब restrict करेंगे M perf पे, तो मुझे मिलेगा restriction of, मतलब S का जो adjoint है, it is the same as T star restricted to M perf, जो यहाँ पे लिखा हुआ. So एक और चीज also, yeah, as a conclusion of the above, so for all x belonging to M perf, S star composed to x is equal to St star composed to x, but that is the same as T of T star, because इसका action वही है. अब चूंकि T जो है वो normal है, this is the same thing as T star T of x, but then I can write it as T star S of x. Again, T star when restricted to M perf would be S star. That is the definition जो हमने अभी किया. तो उसका मतलब S from M perf to M perf implies that this is a normal operator. And dimension of M perf is equal to n minus 1. Therefore, by induction hypothesis, there exists an orthogonal basis B. Actually, basis तो होनी ही चाहिए, लेकिन orthogonal होगी because of lemma 2. क्योंकि वो जो eigenvectors होंगे, they will form a basis, of course, but they will also form an orthogonal basis. Basis B of M perf consisting of eigenvectors of S, but they are also eigenvectors of T, because S is just the restriction of T, which are also the eigenvectors of t से, चलो उनका नाम अगर हम लेंगे x1, x2 up to xn minus 1. Now this is a basis. These are mutually orthogonal, and this is the basis of nth. Now, okay. Now if I adjoin, say चलो b लिखते हैं. Now adjoining vector या जो हमारा x0 है to b, यानी we get a set of eigenvectors, n eigenvectors of t जो होगा x0, x1 up to xn minus 1 that are orthogonal. Why? Orthogonal इसलिए होंगे, देखो ये तो आपस में orthogonal है ही, लेकिन ये contain करते हैं m perp में, है ना, और x0 जो है वो m के अंदर है, तो x0 इन सब के साथ orthogonal होगा. तो these are all mutually orthogonal vectors, n vectors, and hence are linearly independent, क्योंकि orthogonal vectors are linearly independent. And therefore form a basis of H, क्योंकि n vectors हैं H में that are linearly independent और उसकी dimension n है. Therefore they must form a basis of H. And since they are eigenvectors of T, therefore T is diagonalized. मुझे लगता है इसके साथ ही हमारा सिलेबस खत्म हो गया. सिर्फ मुझे जहां तक याद है हमने मैंने तुम्हें कुछ होम असाइनमेंट्स दी थी, शायद एक ये इट वाज रिगार्डिंग दिस. मैं वो होम असाइनमेंट ही रखता हूँ क्योंकि होम असाइनमेंट में तुम्हें 5 मार्क्स होते हैं. एक तो ये था रिगार्डिंग द CAB इज सेपरेबल, ये मैंने दी होगी डेफिनेटली. अगर नहीं है तो क्योंकि मुझे दिमाग में आ रहा था ये मैंने कराया नहीं. दूसरा इसी के रिगार्डिंग डुअल ऑफ CAB. अब मैं तुमने पढ़ा है ये रीमान स्टिल्जीज इंटीग्रल?
नो
नहीं पढ़ा है. इसका मतलब ये तो खैर तुम कर सकते हो, लेकिन इसके लिए चाहिए वो स्टिल्जीज इंटीग्रल का आइडिया. इसका मतलब नेक्स्ट टाइम मैं ये कराऊंगा व्हेन वी फिनिश इट. ठीक है, क्योंकि ये तुम्हें नहीं आएगा विदाउट नॉलेज ऑफ रीमान स्टिल्जीज इंटीग्रल. वो कुछ उतना डिफिकल्ट नहीं है, समथिंग सिमिलर टू रीमान इंटीग्रल. सो वी वुड डू दैट. ठीक है, डुअल ऑफ CAB को ऐसे ही रखते हैं, ये तुम खुद करोगे, ये मैंने दिया भी होगा टू शो दैट दिस इज अ सेपरेबल स्पेस. सो डू दैट. किसी भी जगह से ये तुम बुक में होगा, ये भी होगा ऑलमोस्ट सभी बुक्स में, लेकिन ये तो खैर तुम समझ जाओगे, इसमें कुछ है नहीं. लेकिन इसमें थोड़ा रीमान स्टिल्जीज का आएगा. सो लेट मी एंड इट हियर, और शुड वी कंटिन्यू? हाँ, इसके रिगार्डिंग कोई क्वेश्चंस तुम इस वक्त मुझसे पूछ सकते